Okay, chapter 4, we start talking about chemical reactions. Before we start talking about that, we have to talk about dissolving things into water, which is where we're going to be taking place of our chemical reactions. So the way we classify things that we dissolve is whether they will conduct or not conduct electricity. Pure water is not a conductor. Now, if I said I was pouring water onto the floor and putting in a loose electrical line in there, I would be crazy to step in there, even if it was still distilled water, because of the fact that it's probably picked up ions just from being on the floor. However, if I got into a nice clean container, like a swimming pool that had been purely cleaned and filled with distilled water, and I could get into that with an electrical outlet and still be okay, because pure water is not a conductor. Only when we dissolve substances into water does it become a conductor. Now, so we classify things that we dissolve into two major categories. Electrolytes, which means when they dissolve, they cause the water to conduct. And these tend to be the soluble ionic compounds, which we're going to get into what this means in a few minutes. And then non-electrolytes, which is when a substance dissolves, gives a non-conducting or a very poorly conducting solution. And these tend to be molecular substances. Okay? And so we'll see that too. Okay. So here on the slide, you can see the fact that I have pure water. So this is distilled water, okay, not just tap water, but distilled water. And I have a 9-volt battery connected up and a light bulb, and you see the fact that there is no light coming out. I add sodium chloride to this beaker, okay, not a whole lot of sodium chloride, and all of a sudden the light bulb will light up. That's the difference between non-conducting and conducting. And sodium chloride happens to be a strong electrolyte, which we're going to get to in just a second. So if I have an electrolyte, okay, and I have strong electrolytes and weak electrolytes, okay, a strong electrolyte consists almost entirely as ions, whereas a weak electrolyte only gives a relatively small part of ions, okay. So the difference is when I write the reaction, okay, and so I put NaCl, which I've already said was a strong electrolyte, into water, then I get Na plus Cl minus, okay, and this is hydrochloric acid over here. The one over here that the light bulb is just barely written is ammonium. I'm going to write it down as NH4OH instead. When I put it into water, this time I have two arrows, one going forward and one going backwards, okay, and so it forms NH4 plus OH minus. So some of it forms ions, but with this double arrow means that this is also still present in my solution. And you can actually see the difference in the intensity of the light. So how do I decide if something is a strong electrolyte or a weak electrolyte? Well, for ionic compounds, basically it's based on the solubility. Okay, so soluble compounds means that the substances are likely to dissolve into a solution. Insoluble means they're not likely to dissolve in a solution. And the solubility rules allows us to make a prediction as to whether something is soluble or insoluble in water. Okay, and so these rules are 1 through 8. And if you think of that, it says rule, but also think about this as being a ranking. Okay, which means that rule number 1 is more important than rule number 2 or 3 or 4 or 5. Okay, so the first thing I'm going to look at is that lithium, sodium, potassium, and ammonium, so the +1 ions in group 1A and ammonium are soluble, meaning the fact that they dissolve in solution, and there are absolutely no exceptions to this. Okay, you'll also know that rule number 1 is the only one in this whole table that is a positive charge. Everything else here is a negative charge. Okay, so when I'm going to do these problems, I'm going to look at this and I'm going to look and see what the first element is, or ion is, and determine if it's group 1 or ammonium. If so, I don't have to look any further, it is soluble. Rule number 2 is the first time that we have negative charges. This is acetate and that's nitrate, and both of them are soluble with no exceptions. Okay, So it doesn't matter what I have in front of the NO3 or what I have in front of the acetate ion, it will be soluble. Okay? Chloride, bromides, and iodides. Most are soluble, not all now, but most are soluble. The exceptions. Now, I don't really like the way this is written out. What I want you to know is silver, mercury, and lead. Okay? I'm not going to get into the differentiations of those. So silver, mercury, and lead are the three that you need to know. Technically, it's a mercury or a lead 4+, but again, it's more important that you just remember silver, mercury, lead, because those are 3 of the 6 that are going to cause me exceptions. So for all my chlorides, bromides, and iodides, they make them insoluble. Most sulfates are insoluble, except, so that means that for these two, the exceptions are insoluble. Okay, so for these two, the exceptions are insoluble. Okay, and again, you see I have my silver, my mercury, and my lead. Okay, so that's why I said I want you to know those 3. But I have 3 additional ones. Okay, and make those a different color. I have calcium, strontium, and barium. I'm going to need those again somewhere else too. So I'll write those over here. Running out of room. Okay, so those are my exceptions also. So these 6 ions are important for everything that we do for an exception. It's those 6 ions. Okay, now also the fact that now I'm going to draw a line across this table. Okay, so let's see how well I can draw this line. Not very well, but you'll get the idea. Why am I drawing this line? Because up here, these all read are soluble, are soluble, are soluble, are soluble. When I get below this line, so rule 5 through 8, they are insoluble, are insoluble, are insoluble, are insoluble. So that means that my exceptions over here are soluble. So whatever this statement reads, the exception is the opposite. Okay? In reality, because of the fact that all 3 of these have the same exceptions, and they all 3 say the same thing, I would group this into rule number 5, and then there's less rules. So most carbonates, phosphates, and sulfides are insoluble, and the only exception to that is rule number 1. So like I said, rule number 1 is the most important rule. I look and eliminate that first. Okay, so basically most of them are insoluble, except for if it is rule number 1. Okay, and the last one is hydroxide. Okay, so again, rule number 1 overrules here, but again, you're going to see the fact that I have 3 exceptions in addition to rule number 1, which is calcium, strontium, and barium. So silver, mercury, and lead make chloride, bromide, iodide, and sulfates insoluble. Calcium, strontium, barium make sulfates insoluble but make hydroxides soluble. So it's a little bit easier way to remember what these rules are. Okay?